All flight takes energy. It's an important consideration for birds who fly to hunt for food, a matter of survival. Energy cost doesn't always concern humans, but we should weigh the benefits of flying against its environmental impact. The most important feature of an aircraft is its wing. The purpose of a wing is to deflect air downward as the aircraft moves forward. The deflected air applies an upward force to the aircraft that we call lift. Moving through the air and deflecting it downwards causes a drag force, which requires a continual input of energy from the engine to overcome. The propeller blades of a small plane, or the fan blades of a jet engine, behave much like wings do, in that they deflect air, and to a lesser extent exhaust gases. This deflected air causes thrust, pushing the plane forward against the drag force. A plane flies at constant velocity if all the forces are balanced. Lift equals weight, and thrust equals drag. The bigger the lift, and the smaller the drag, the better the plane or bird flies. And the less energy it uses to get to its destination. The only way we can currently carry enough energy to feed this continual input is in the form of hydrocarbon fuel. Only oil derivatives have sufficient energy content per kilogram, although some jets have been flown experimentally with biofuels. When an aircraft makes its initial climb to cruising altitude, it is converting energy from fuel into potential energy. This is the Boeing 747. Fully laden, it weighs 400 tons, 150 of which is fuel. During the aircraft's descent to its destination, its potential energy is used to overcome drag, and to keep the plane flying at a constant, but reduced speed. The flight path is now a steady descent at the standard 3 degrees to the horizontal, and the engines of this 747 are hardly being used at all. The plane is almost gliding. If we know the plane's speed and mass, we can easily estimate the rate at which potential energy is being used in this part of the journey. We can do the same thing with the balsa glider. When you throw a glider, you give it some potential energy by lifting it up off the ground, and some kinetic energy to set it flying. As it flies, at more or less a constant speed, it slowly loses potential energy, and eventually it hits the ground. By measuring the height from which the glider starts, and how far it goes before landing, you can estimate the rate at which the glider is using potential energy. If you measure its mass, you can estimate the size of the drag force. Anyone learning to fly gets to try this with a real aircraft. The pilot of this Piper Warrior reduces power to the engine and kills thrust in a routine training exercise. The plane begins to descend. With no thrust to balance the force of drag, the plane assumes its glide slope downwards. The pilot manages to turn the engine on, and she can now level out. When we do our measurements and calculations, we find that the energy required to move an aircraft per ton per kilometer is always roughly the same, regardless of whether we were talking about 747s, small planes, balsa gliders, or even birds. This is what physics does. It allows us to make connections between seemingly different things. A 747 burns 150 tons of hydrocarbons to cross an ocean, whereas a small glider needs only be lifted to shoulder height to fly. By making these connections, we can come to general conclusions about the energy and environmental costs of flying, without knowing the details of what future aircraft will look like.